Hello, students. This is our last video lecture for Unit 2. And in this, we're going to discuss two concepts. One is percentiles, which we've already done, but we're going to formalize. And the other is boxplots, which is a pretty straightforward graphical technique that is closely aligned to numerical summaries. So let's get started. So the first example I have for you are heights in a classroom. So we have the heights listed above. As you can see, there are 9 heights that were recorded in this sample. So what happened next was the creation of a histogram. And as you can see, the class width is 4, because from 59 to 63, there's a difference of 4. And we count the frequencies within each of these intervals. So between 59 and 63, including 59, but not 63, you can see we have the values of 59 and 62. So the frequency there is 2. For the span of 63 to 67, we have the values 65, 65, 66, and 66. So there are 4 in that interval. And between 67 and 71, we have the values of 68 and 68. And last but certainly not least, from 71 to 75, there's one data value of 71. So that is where all the frequency counts came from. The relative frequency, as you recall, is just dividing the frequency by the total frequency. So that gives us 2 divided by 9, which gives us a non-ending decimal. So it would be 0.22222 all the way as far as you could write and beyond. So we're just going to round that to 22.2%. And then similarly, the other percentages are calculated in the same way by dividing frequency by total frequency. Now, the cumulative relative frequency is where the interest lies in this video lecture. So if you look as you go from left to right across the graph, which we'll see in a minute, or top to bottom in the table, what you'll notice is we're adding up the relative frequencies and accumulating them, right? So cumulative is to gather together. So when you look at the first interval, we're only going to have that first interval going left to right. So it'll only be 22.2. But then the next cumulative frequency will include the next interval or the next bar in the histogram or the next value in the table. So that's going to get us up to 66.6 because we're adding the 2 relative frequencies for those first 2 rows. And then the third row is 88.8. The last row is 99.9. Sometimes there's a rounding error. You should be very close, if not exactly at 100%, to ensure that you have all the data. Because if you accumulate it all left to right, by the end of that, you should have everything. So this is simply a rounding error due to the decimals. Now, when you go left to right, you also start keeping track of percentiles. So these percents in the cumulative frequency are our percentiles. So what does that mean? If you look at that 88.8, keep that in your mind. That's basically 89%. So when we look at the graph, the 89th percentile is 71 because that's where that bar ends. So what happens is percentile is simply saying from the start on the left-hand side or the top of the table all the way over until you accumulate that much relative frequency, that will be your percentile. So hopefully that's clear. So those are how percentiles work. There's a very specific version of it in boxplots that we're going to discuss next. So boxplots are percentiles of the data in a way that's very informative. So the goal of a boxplot is to take the data and chop it into quarters. So there are going to be these things called quartiles. Now, what is a quarter? A quarter is 25%. So 25% of the data is in each of these spots. So if you see from the minimum to Q1, 25% of your data is in there. From Q1 to the median, 25% of your data is there. From the median to Q3, which is the third quartile, you have 25% of your data. And then from Q3 to the max is the last 25%. And if you add 25% 4 times, you get 100%. So again, that's 100% of your data. This is how we display it. We've already talked about median in our last video. So you should recall that median is splitting the data 50-50, which now is even more apparent with this graphical display. To the left of the median is 50% of your data, and to the right of the median is 50% of your data. There's this part in here about outliers being determined by 1.5 times past the distance. We'll discuss that in a very, very particular example, so it's clearer. But if you are too far away from the box plot, when your values are far to the max or far to the min, and not really close to the chunk of the data, then those will be considered outliers. So they're strange values that lie too small or too large. So here is an example. In this example, as you can see, I took the heights that we discussed earlier that's in the histogram. I laid them across the top here. So again, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 values spanning from 59 to 71. So if you look at this box plot, the easiest ones to start with are the lowest you would do a line. So there's 59. And the highest value you'll put a line. So there's 71. So as you can see, that's where the box plot will start and end, because then it has all of the data within those frames. So where do we get these other values? Well, we've already discussed the median, and we know the median is in the middle. So as you can see right there, 66 is where another long line is drawn. And because it's called a box plot, there's going to be a box in the middle. But that is the center line that we draw at 66, the median. So where do the other values come from? So those ones are a little harder. Now remember, we're trying to chop up the data into the same size pieces. So that's 25% of our data. So if you look, what we're really doing is to the left of 66, we have 4 values. And to the right of 66, there are 4 values. We want to chop those in half again to give us quarters. So what would be, so the first quartile is sort of like the median for the left side, and the third quartile is like the median for the right side. So the first quartile will fall between 62 and 65, because that would cut that in half and leave 2 data values to either side. Remember, if we have an even number of values, the median is between 2 values, not any one of the values. So that one is 63.5. And on the other side, between 68 and 68, you have 68. So here it chops it into 1, 2, 3, 4 different segments, all containing 2 data points. So that means there's 25% of the data in each of those boxes. And that's what gives us the first quartile. And that's what gives us the third quartile. And those are the other lines that close off the box. The lower one is at 63.5, and the higher one is at 68. All right, so let's discuss outliers. So using the same data, we're going to calculate this thing called the interquartile range. So the interquartile range is exactly what it sounds like. It is inter, in between the quartiles. All that means, and then of course range we know how to calculate, it's subtraction. So the interquartile range is simply a subtraction of the quartiles. The high one at Q3, which is a third, minus the smaller one at the first quartile. And that'll give us a distance of 4.5. Now the definition of an outlier is if it's 1.5 that distance to either the left or right. So 1.5 that distance, so that distance is 4.5 from the subtraction. If we multiply that by 1.5, we get 6.75. And that is the value that we move in either direction. So here, just to make it clearer, see this brace here? That's 1 interquartile range. And then I added another half. That's why that other brace is up there, but cut in half. That moves us to the point where if anything is further out beyond that last brace, it would be considered an outlier in the lower end. And we're going to replicate that on the higher end. So these are called fences. And what that means is it's an imaginary line where if you're outside that fence, you are an outlier. And if you're inside the fence, you stay attached to the box plot. All right, let's do one more example. This is test data that's fictitious from 2.14 to try it in your workbook. And we have 2 statistics courses, and we're trying to figure out which one would we rather be in. So for test A, we're going to take those data values and again, put them as a frequency. We can do a relative frequency and cumulative frequency. So this is just another sample. If you want, you can go back, take that data and try to recreate this yourself. It would be really good practice. I highly recommend. So this is one table. And again, on the far right side, the cumulative relative frequency are actually also our percentiles. And as you can see, we have 100% at the very end, which means we do have all of our data. We also recreate this for test B. So if you want to practice with test B data as well to create this graph, that is also a good exercise. And now I've utilized both these tables to do a side-by-side histogram. So we can look at the 2 distributions. And they're going to look a little funny this time. So here, this is not as informative as we would like. One thing we can say is it's not very symmetric, right? There's a big gap in the middle for B, and A has a dip. So it's not centering in a bell shape at all. So it's some other kind of distribution. And if you recall from several videos ago, I said if it's not symmetric, then this is not very useful, right? The mean sort of fails as a great measure of center because it loses its meaning when the data is far from symmetric. So what could we possibly do? Well, we're going to rely on the median. And since we're relying on the median because of the strange shapes of these distributions, because the median becomes important, so do box plots. So we're going to set up box plots. Apologies that I couldn't fit the data straight across. So it actually ropes down. So if you look, 65 goes all the way to 80, but then loops down to the next line, 81 to 99. That's all part of the same data set. On the plus side, listing it like this makes it very clear where the medians and the quartiles are, because cutting the data up is a lot easier when actually you have the same number on top and bottom, because if their same number of values are on the top row compared to the bottom row, then that means they're the same amount, which means we've cut the data in half. So clearly between 80 and 81 is where the median lies. And again, for test B, between 80 and 80 is where the median lies for test B. So respectively, in test A, we have 80.5, and in test B, we have 80 as our medians. Now, remember, the next part, the quartiles, chops it in half again. So if you have half of a half, that gives you a quarter. So all we're doing is we just keep chopping the data in half. We do it once for the full set, and then we cut each of those pieces in half again to get our quartiles. So if we chop the data in half again, as you can see, we have 5 and 5. So that is an even number. So it's going to be a value that falls between the two. In this case, between 69 and 76, if we average those two, we'll get 72.5, and that would be right in the middle of those two values. And the other one is very easy to come up with. 90 to 91 must be 90.5. Similarly, for the bottom, the first quartile must fall between 72 and 73, which gives us 72.5. And for the third quartile, it has to be the value directly between 92 and 95, which in this case is 93.5. So make sure you have all of these values in your head and remember them or write them down, because next we're going to put them in the graphical display and you'll see all these values pop up. The other two values we need for each set is the minimum and the maximum. So for test A, we also want to record 65 and 99. And for test B, we want to keep track of 68 and 100. So with that in mind, as you can see, test A goes from 65 to 99. So here's 65 and up there is 99. Test B goes from 68 to 100. So test B is 68 to 100. It's the top box plot. And if we compare these, they're quite similar. So really, it's hard to determine a clear winner for which statistics course I would want to be in. I would likely pick the lower one because the median is higher. But again, on the upper one, 50% of the data spans from 80 to 100. So that means half the class is scoring in that. But both of these classes seem to be doing pretty well. In some examples and instances, there would be a clear winner where one box plot would be much higher in the values than the other. But in this case, they're pretty comparable. So now you've had the opportunity to also interpret a box plot. There's going to be lots of practice in the Excel workbook on this. And also, this is a critical skill and concept that you need to know to help you analyze real world data going forward. So make sure you understand box plots. They are used in reporting of data, and they're very useful when the distribution is very skewed and not at all symmetric. So I'm going to stop here. That's it for Unit 2. Congratulations, you made it to the end of Unit 2. And I can't wait to work with you next week on the next 2 units. I'll see you then.